my name is Yiğit Küçük, and I'm going to be presenting our paper with Tim Henderson and Andy Podgorski that details our fault localization algorithm, Unival. First, let me introduce the problem of statistical fault localization, or SFL for short. SFL is a partially automated approach to localizing faults in programs. SFL techniques input execution profiles for a set of program executions, such as code coverage profiles, together with indications of whether each execution succeeded or failed. To this data, the techniques apply statistical measures of association between the failure data and profile data in order to compute what are called suspiciousness scores. These scores are used to rank program statements so that the ones with the highest ranks are the most likely to be faulty. Programmers are supposed to use the ranks to guide the debugging effort, and intuitively, statements that are covered by mostly failing runs are more suspicious. In essence, we can say that SFL techniques attempt to estimate the average causal effect of executing individual statements on the occurrence of failures. In 2010, Ba et al. Showed that the confounding bias, which is a bias that researchers have traditionally worried a lot about, could distort the suspiciousness scores computed by the SFL metrics. To reduce or eliminate confounding and other forms of bias, researchers use causal inference techniques. Normally, in a study, we get to observe the value of an outcome variable for only one value of the treatment variable. The outcome under another treatment value is counterfactual, counter to the facts. This is called the fundamental problem of causal inference. To guide the causal inference process, researchers use causal-directed acyclic graphs, or causal DAGs for short, in which the vertices represent study variables and the arrows represent causation. Confounding bias is bias due to a common cause of a treatment variable and an outcome variable. In the DAG shown on the lower right of this slide, C is a confounding variable that lies on a backdoor path from the treatment A to the outcome Y. This path begins with an arrow into A, and it creates a flow of association between A and Y, which distorts the estimated causal effect of A on Y. To eliminate confounding, we can block all backdoor paths, for example by stratifying our analysis on the value of C. Causal DAGs must satisfy the causal Markov condition, which requires that given the value of its parents, each variable is conditionally independent of its non-descendants. Although most SFL techniques employ code coverage profiles, value-based techniques use value profiles, which record the values of program statements. Our method Unival is value-based. The treatment variable is the target of an assignment. For example, for the assignment statement in the box, the treatment variable is A, and the outcome is the failure or success of a program execution. And the potential confounders are the variables B and C, as well as are used in the statement. An example of the value-based techniques is the value replacement technique, which replaces the values used in a statement during one execution with values from another execution. The statement receives a high suspiciousness score if the replacement of values at that statement tends to change failures into successes. Predicate switching is an interventional technique that is reminiscent of value replacement technique. Predicate switching forcefully alters the output of a branch condition in a failing run until the switching produces the correct output, then reports the predicate as a critical predicate. Unfortunately, both techniques require re-executing a program many times with different value assignments or branch conditions, which are expensive. We thought that by integrating information from both predicate outcomes and variable values and utilizing machine learning and the causal inference methodology, we can have a more accurate estimate of the true failure causing effect of program statements on program failure. Unival, in a sense, simulates the value replacement technique without the costly re-executions of the program many times. It does this by predicting individual counterfactual execution outcomes under a contrast of treatment values. The predictions are made with a machine learning model. We use a random forest model. The model is trained on treatment, confounder, and outcome values from a sample of executions, and the trained model is applied to the same confounder values but different treatment values in order to predict counterfactual outcomes. So for each treatment value that wasn't used in a particular execution, we can simulate using that value by plugging it into the model and predicting the counterfactual outcome. The average failure causing causal effect is estimated by averaging over individual counterfactual outcomes. Let's take a closer look at the Unival algorithm. First, the program P is modified by transforming branch predicates into assignment statements, and then the resulting program is instrumented by the guidance of a program representation called Gated Single Assignment Form, or GSA for short, which is an extension of Static Single Assignment Form, or SSA for short. In both the GSA and SSA forms, each variable is assigned to in only one statement. GSA form creates shadow data dependencies that can be used to replace control dependencies when forming a causal graph of a program. This helps ensure that the causal graph satisfies the causal Markov condition. The instrumented program is then run on a set of test cases to produce value profiles and other information necessary. Numerical variable values are binned and string variable values are clustered to produce a small number of representative treatment values. The modified value profiles and test outcomes are used to train a random forest regression model for each assignment statement. And the trained model is used to predict the counterfactual outcomes for the representative treatment values. Individual causal effects are estimated for all pairs of representative values, and average causal failure causing effects are estimated by averaging the individual causal effects. The maximum of all pairs of representative treatment values for a statement is its suspiciousness score. We conducted an empirical evaluation on Unival, which we compared it to 7 competing techniques. Each of these techniques has performed well in a recent study. We used the subject programs in the well-known defects forgery repository, version 2.0, which contains over 800 faulty versions of 17 substantial programs. This diagram shows our empirical evaluation process. The defects forgery programs were transformed and instrumented as described earlier. Each program was run on its test suite to produce the value profiles, test outcomes, a causal DAG, and other information necessary. This data was input to the scripts we wrote to implement the SFL techniques we compared, and then the results were compiled and analyzed. This slide shows our raw results, averaged over all buggy versions of each subject program. We compared the techniques using 2 measures, examination score and hit at n for n equals 10 and n equals 5. We only showed the results for hit at 5. Overall, Unival had the best performance as shown by the row labeled average in the left table and the row labeled overall in the right table. The results were significant at the 0.05 level. From start to finish, Unival takes about 56 seconds compared to 660 seconds for predicate switching. This figure represents exam scores graphically. Each bar represents the percentage cost reduction in terms of exam score that was achieved by Unival over a competing technique. The bars below the 0% line are cases in which Unival did worse than a competing technique. As the figure indicates, Unival performed best overall. We also investigated why Unival performed as well as it did. In the absence of confounding, the joint distributions of the covariates used for the confounding adjustment should be similar in all treatment groups. This desirable condition is called covariate balance. It routinely occurs in randomized experiments, but typically does not occur in observational studies like the fault localization studies. To better understand the effect of covariate balance and imbalance on the performance of Unival and coverage-based SFL, we measured the degree of imbalance in data sets for faulty defects forgery versions. We related the covariate imbalance to the cost of fault localization as measured by the exam score and used a well-known technique called OKI to represent the coverage-based family. For simplicity, we used only the program versions that contain a faulty branch predicate. This figure shows the results of our study on covariate imbalance. Note that for the x-axis, larger values represent greater imbalance, and for the y-axis, larger values represent higher costs for fault localization. The results indicate that higher fault localization costs are associated with greater imbalance. This is consistent with our previous results indicating that covariate balance is associated with lower estimation bias in observational studies. However, it is evident in the figure that when the covariates are imbalanced, the cost of fault localization with Unival is usually lower than with OKI. This is due to the fact that Unival adjusts for confounding and therefore mitigates the effects of covariate imbalance. Thank you very much for listening to our presentation.
Hello, everyone. Welcome again to the session about fault localization. I'm here with two of the authors of the third paper, and we have Heath and Tim. And so please use the chat to ask the questions to the authors. And again, while you are thinking to your questions, let me again remind about the breakout room of this Q&A session, where you will have the opportunity to interact directly with the authors. And okay, we wait for your question. In the meanwhile, I will ask a question. Something I would like to ask is it possible to use your method to provide information not only about the location, but also some information that may help the tester to interpret why a suggested location is faulty? So because one of the issues with fault localization is that once you generate just the information about the location, still the tester, the engineer, has to understand the fault is really there, why this location has been recommended, and so on. So I wonder if, based on the analysis that you perform in order to isolate the various locations and to rank the location, if you see also any opportunity to provide something more than just the location to the test.
Well, so far on statistical fault localization, what has been done was just the location, and that's what we have done here. Once we've established this, it's a good idea to think about, maybe giving them the reason. So far, the reason would only be that, since we have two counterfactuals and then they disagreed with each other, and that's how we are scoring the elements as well. So if the score is high, that means that, there's something wrong there.
Yeah, and to add to that, on the counterfactuals, if you have with the variable values, we can potentially, it's not something that we've tried yet, but we can potentially provide the representative values that are associated with failure as a way to give like a hint of what's going on.
Okay, yeah.
Definitely a good idea.
Good. Okay, still I don't see questions in the chat, so I will exploit this opportunity to take another question. Okay, I see now a question is coming. So Christina is asking the following question: is the approach available for use by practitioners? The tool, code we can download and run, etc.?
Yes, Christina, we have the artifact for this. If you go to our paper and look at the data availability section, you'll find the link there. It's a Zenodo repository that we've uploaded that to. It has a README there, but I'm happy to take your questions if you have any, if any difficulty by using it. I've just posted my email there. Feel free to email or use our email from the ELISAs from the paper.
And we'd be like happy to interact with you and find out more about your use case and what you're looking to get out of fault localization.
Nice one.
Okay, good, thank you. And still going to ask my question. Since the analysis that your approach performs in order to localize the statements is kind of, I would say, more sophisticated than the standard spectrum-based fault localization, I wonder about the runtime. So what is the difference in terms of the cost of running this analysis with respect to, let's say, running spectrum-based fault localization? Is the delta significant, or are they kind of comparable in terms of the cost of running the analysis?
So it's a good question. We do have some overhead because of the models that we're fitting for each variable. And some of the instrumentation obviously is costly. We were thinking that it would be like about 20% to do this instrumentation and run it. And it takes, on average, less than a minute to run ours, where it is about 5 to 10 seconds to run the spectrum-based fault localization, the coverage-based methods or the traditional methods, just because they are simple calculations. and ours need to fit a model and then actually make predictions on that. So there is some overhead, but it's not negligible as well. But I think it is a good cost to, it's a good trade-off to have an accuracy versus, the run times.
Okay, I see. And can the technique be used also with multi-locations bugs?
Yeah, so, well, the assumption with any multi-location bugs in our field, I would say, is to find the top bug. Once you locate it, rerun the program or rerun the algorithm again and find the next one, kind of thing. So that should be the next step on, seeing if we can do that efficiently. I think that's like a future work for having the multiple bugs to do that.
No, what I mean is not having multiple bugs, but having a bug that spans multiple locations. Is this, kind
yes,
of
hitting a location on the multiple locations, and then you would be considered you would localize the fault.
So sorry, say it again.
So if there's like a multiple, the bug that points to multiple statements, you would be finding one of the statements that is faulty, and then that's what you generally are.
Okay, you assume it's enough to identify one of the locations.
Correct.
Nice.
Yeah, it corresponds to the min rank score in the Steinman paper, versus like there's a couple different ways you can do it, but they all have kind of, there's a lot of assumptions baked into all those evaluation methods. So this is the assumption we chose. Yeah,
I see. Good. Let's see. I don't see for the moment other questions. Chat. We still have a few left. If anyone would like to ask a question, I think I have asked already mine. So let's see if someone would like to ask a question. Still a couple of minutes available. Otherwise, if there is no more question in the audience, we can close the Q&A a couple of minutes earlier. Anyway, the end of the Q&A session, again, the opportunity to join the breakout room and interact with the authors. Okay, again, Christina, the question is, which programming languages do you support?
The one that we can support right now is Java, and it's a general approach that any Java program should work. And we chose that because of the real false repository that we use the defects for. The repository was in Java, but we have tried this on toy Python programs, for example, and it works fine over there as well. So the first future works planned, and Adriano, is to be able to cover, for example, loops and arrays and objects. For example, with this, we only have strings and predicates and variable assignments right now. So having, for example, a loop would require more sophisticated programming to be able to get the causal graph right. So that's what we're trying to do, and then some improving the efficiency of, for example, running for each variable the models. For example, we could make that parallelly running, like in parallel. So that's like another improvement on the tool side of things, the application side of things. So those are the ones that we're planning in the near future.
Yeah. And another one that we're thinking about is improved instrumentation accuracy, scalability to have lower overhead for the instrumentation itself.
Okay, there is a question also by Hridesh. Would loop invariance be needed to cover loops?
I am not sure what that asks. With loop invariance, what does that mean in that context?
I think if you need to compute the loop invariant in order to handle loops in the analysis.
I don't think that you would need to do that sort of analysis or have programmer supply invariants for the loops. It's more about how you structure the causal graph and fit it into how you structure the graph for the loop, because a causal graph has to be a cyclic graph, and the loop is obviously a cyclic graph. So you have to break cycle, which is why we want to improve this.
I think we are going to be cut in a couple of seconds. Thanks, everyone.